Thank you, Motozuka Sensei. Good afternoon, everybody. Before I start, I'd like to introduce myself. My name is Mega Novita, the head of Science and Technology Research Center of Universitas PJRI Semarang, or called as UPGRIS. Previously, I studied in Ogasawara Lab for my master and doctor courses. I also enrolled as a postdoctoral researcher in there and in Chonbuk National University under the guidance of Kim Yang-soo Sensei, who is also a member of the DVX Alpha Society. Since 2011, I've been actively joining the DVX Alpha annual meeting. Here I show you some pictures, and it was very, very good memories. And it was in Shizuoka. And here is 2012 in Fukuoka, 2013 in Kyoto, 2014 was in Nagoya, but I don't have any pictures of that. And 2015, I started my job in Indonesia and I couldn't attend the DVX Alpha meeting, but I joined again in 2016, that was in Tokyo. Then 2017 in Himeji, 2018 in Nagaoka, and 2019, that was the best moment in my life. It was in Indonesia. At the time, my university was the organizer. Thanks to you all, we hosted the event successfully. This is the picture of our university. We have 7 faculties, consists of 21 undergraduate programs and 5 graduate programs. And this one is the picture of my students. And I'm glad and also honored because today in this very nice opportunity, my boss, one of my boss, Dr. Seno Warsito Sensei, attending this meeting. So you already know before. And in UPGRIS, I pioneered an international journal called ASET, an Advanced Sustainable Science, Engineering, and Technology. It is still new, but I'd like to encourage you to submit your articles in this journal. Okay, this opportunity, I'd like to talk about a study on the optical characteristic of transition metal ions in alpha alumina crystal using DVX alpha and DVMA method. Then I'd like to give you all an illustration. In our daily life, we are often to talk about phosphor. It's not one in the spinach, but it's actually any material that when exposed to a radiation emits visible light. Here are the examples of compounds. In a normal condition, it appears just white like a sugar. However, when they are exposed by UV light in 254 nanometers, they emit different colors like this. Then, in fact, phosphors are important. They are used in many applications such as backlighting, automotive, signage, and of course, general illumination in housing, school, office, and etc. Especially in general lighting, long time ago, we used candle. And then after the electricity was discovered and Thomas Alva Edison invented lamp, we use incandescent lamp. Since it is inefficient due to the energy loss in the form of heat, we use fluorescent lamp, which is very efficient, but unfortunately, it consists of toxic mercury vapor. Then we started to use light emitting diode or LED. Here I show you the picture of white LED lamp. If we open it, you'll see the electronic components like this. The small square chips here are the most important part. Here, the yellow chip, the yellow square here. It consists of blue LED chip coated with yellow phosphor. So this is the structure of inside the current white LED. Blue LED emits a blue light and converted into white light by the yellow phosphor. However, the color is a little bit bluish. It is because it lacks of a red component. And compared to daylight spectra originating from sunlight, the current white LED lacks red component. That is why we see the bluish white light. So why do we need red components? Well, do you notice when we mix all paint colors, we will get black? Yes, because there are 2 different types of color mixing, subtractive and additive. Subtractive is for paint color, absorbing all pigments, while the additive is for light source. You see there are three pigments colors, however, the results of color mixing is different. Actually, there are many ways to get the ideal white light, such as mixing all LED chips like red, yellow, and blue. But this way is too expensive. Since the current white LED constructed from one blue LED chip coated with yellow phosphor, then adding red phosphor is the easiest and cheapest way. The blue LED chip emits blue light converted into white light by both yellow and red phosphors. By this structure, we will get the ideal white light. So what is the ideal white light that we want from LED? The quality of white LED lamps generally depends on some parameters, such as the color coordinate, color temperature, and also color rendering index. Color coordinate specifies the appearance of an object to human eye. Color rendering index indicates the ability of light source to show the true color of an object. Then the color temperature indicates the temperature of the filament in case of light bulb, or the temperature of the emitted light in the case of fluorescent and LED lamps. It is in Kelvin. Then, because of that, many researchers are trying so hard to find the suitable materials for the red phosphor used in white LED. We mostly concentrating on the transition metal and rare earth ions. We reactivated those transition metal ions in host crystal compounds. For the host crystal of fluoride compounds such as K2SiF6 or in oxide compounds like Al2O3. You can imagine in this world, the combination of dopant and host crystals are actually too many. Since the trial and error experiments are rather ineffective, time-consuming, and cost highly, therefore, simulation using computer is really helpful. It is also very fortunate for me as well, because in my university, we don't have enough tools to do experiment. That is why simulation is the best option for my research. This figure illustrates the research hierarchy of experiment, industry, and theoretical, also academic. And many people are doing experiment. Few people have their research which can be applied in industrial scale. And less people are doing theoretical work. So this is our chance to get our work stand out. For the interpretation of optical properties and the multiplet energies, many approaches have been used. For example, the empirical approach, ligand field theory proposed by Tanabe Sugano. In the octahedral crystal field, 3D orbitals split into two degenerate levels called EG and T2G, which the energy splitting between them called as crystal field splitting or 10dq. And their multiplet energies are has been summarized and known as Tanabe-Sugano diagram. Some semi-empirical approaches, for example, Watanabe and Kamimura, who combined the LDA and LFT, Daul, who used the first principles calculation based on DFT theory, Seiho, who combined a hard revoke type calculation and configuration interaction, Groot, who used crystal field multiplet calculation for SANS analysis. The last two approaches here are the non-empirical methods which we studied so far. Here I show you the history of DV method. DV method was first developed by Professor Ellis in 1970s in Northwestern University, and some of his students developed many approaches like DMOL, developed by Professor Daly from Switzerland, ADF by Professor Behrens from Netherlands, and our great Professor Adachi developed DVX alpha in 1978 from Kyoto University. And finally, DVMA method has been developed by Ogasawara Sensei, Kwansei Gakuin University. But actually, the development of DV method has been done by many researchers. So, in brief, the software DVMA, discrete variational multi-electron, is pictured in here. And this is very useful to determine the spectral characteristic of a material. Then the discrete parationality electron TVME versions, there are two, for the non-relativistic and the relativistic one. For analyzing the transition metal ions, we use non-relativistic one, but for rare earth ion, usually we just use a relativistic version, because in the transition metal ions, the relativistic effect is not so influenced, so can be neglected. Here is my list of publication related to alpha aluminum. So if you are interested, you can download it and read it later. All of them are about alpha aluminum. Okay. In the case of 3D3 ions doped in crystal, the energy levels in octahedral crystal field are shown in here. There are some doublet states and quartet states. Quartet A2 is the ground state. The transition from ground state to quartet T2 and quartet T1A are responsible for the absorption process, while the transition from doublet E to the ground state quartet A2 is responsible for the emission process. In the search of novel red phosphor materials for white LED, manganese 4 plus doped fluorides materials such as K2SiF6 or K2TiF6 have been shown to have good luminescence properties. However, since fluoride materials are sensitive to high temperature and high humidity, therefore red phosphor based on oxide materials are desired. So the purpose of this research is to investigate the optical characteristic of transition metal ion doped in alpha alumina in detail, including molecular orbital energy, multiplet energy, absorption spectra, the pressure dependence, and also the quality of the emitted light, which can be represented by the color coordinates. As the calculation for molecular orbital energy, we utilize DBX alpha method. And for the many electron calculation, to calculate the multiplet energy and also absorption spectra, we use DBM method. During the calculation, we also consider some effects such as energy correction, configuration dependent correction, CDC, and also correlation correction, CC. Other than that, okay, before I explain the CDC, the other effect, here CDC explanation. CDC corrects the energy difference between configuration in the left side, and then CC corrects the energy difference between the multiplet split. So other than CDC, CC, I also consider lattice relaxation effect. So basically when we submit one transition metal ions or any ions to the system, then the bond lengths are changed depending on the material itself, like can be shorter or longer. So there are several ways to estimate the lattice relaxation effect. The simplest one is by Shannon's crystal radii. You can see the formula like this. And we also studied the combination of Shannon's crystal radii with EXAFS experiment. And we also investigated the geometry optimization using CASTEP. Fortunately, CASTEP can also be used to predict the pressure effect. The first part of this talk will be D3 ions in alpha alumina. I constructed model cluster consisting of 63 atoms from alpha alumina crystal structure data. We can obtain it from Find It software. Then here is the picture for molecular orbital MO energy without considering lattice relaxation and with considering lattice relaxation effect. The most important thing is without lattice relaxation effect, we see that the impurity levels T2G and EG here mix with conduction band in the case of vanadium 2+. For the other materials, they are fine. But just in case of vanadium 2+, it should be solved, because if we just use model like this, we cannot calculate the multiplet calculation or CI calculation. So we have to separate them. So we perform the so-called orbital relaxation effect, we perform excites half electron tentatively like this. So from T to G to EG states. Then after we perform the orbital relaxation, we obtain the spectra, absorption spectra like this. There are no difference with in the case of chromium 3 plus or manganese 4 plus, but in the case of vanadium 2 plus, the absorption spectra move to the lower energy. Then this is the results with different computational condition. We see that the calculation considering all effects agrees the experimental very well. Okay, here in the case of manganese 4 plus, because lattice relaxation effect is 100% and CC is 1, that means no correction at all in the case of manganese 4 plus. But for the case of vanadium 2 plus and chromium 3 plus, lattice relaxation, CTC and CC improves the energy. So here, if we picture the multiplet energies of D3 ions in alpha alumina for U band and Y band, then we will get increasing tendency of both U band and Y band in the order of vanadium 2 plus, chromium 3 plus, and manganese 4 plus. Now we are coming to the geometry optimization of Ruby under pressure, which was performed using CASTEP code. In the case of non-optimized cluster, we just obtain the crystal structure data with pressure, already with pressure from Find-It software. The pressure is ranged from 0 to 113 GPa. But in the case of optimized cluster, we just use 0 pressure of alpha alumina, and then we adjust the pressure by ourselves using CASTEP. And we get the optimized structure like this. So here is the optimized ALO bond length. Since there are 2 different types of bond length, like D1 and D2, D1 is for the shorter bond length, while D2 for the longer bond length, we distinguish them by D1, D2, and the average. The black symbols here are the experimental data. You see the all bonds here decrease as the increasing pressure. And here is a picture of the optimized transition metal oxygen bond length for chromium oxygen and manganese oxygen like this. You see chromium oxygen bond length are longer than manganese oxygen bond length. Next, we are coming to the discussion of chromium 3 plus in alpha alumina under pressure, especially based on many electron calculation using DBMA method. Okay, many electron calculations. So these are the MO energy levels using DVX alpha method for Ruby non-optimized cluster and the optimized cluster. The relative energy difference between T2G and the valence band becomes closer here. And this crystal splitting 10dq become also smaller compared to the non-optimized and optimized cluster, but the impurity levels are increased. Next, this is the picture for energy diagram of Ruby under pressure for non-optimized cluster without and with CTCCC, optimized cluster without and with CTCCC. The symbols here are the experimental data, while our calculation are shown by lines. So the doublet states are shown in R, R prime, and B, while the quartet states are shown by U and Y bands. Then we can see here the lattice relaxation and CTCCC give an excellent agreement with the experimental data. So you see here, they are very, very close to the experimental data. And this one, we investigated further for C factor, lambda, C lambda, JAO, JMO, and also J effective. They are the Coulomb repulsion effect. You see the GAO, JMO, and lambda here increase as the increasing pressure. But since the C factor, the correlation correction decreased, then J effective is also decreased. This is because it implies that there is competition between the Coulomb electron-electron repulsion and the correlation correction, which decreasing trend which is suitable with the decreasing trend of doublet states. Okay. In this part, I will show you the results of multiplet energy calculation based on one electron DVX alpha method. We know that it has been almost impossible to calculate multiplet energies based on one electron approach, but here we successfully calculated them at least for R-line energy. Onishi Sugano in their report in 1982, they reported that they have been successfully estimated the chromium oxygen bond length versus multiplet energy and pressure for chromium 06 material, and they compared the result with the data of Ruby. But actually their calculation accidentally agree with the experimental data. I will show you the reason. So in their calculation, they calculated the R-line energy based on the gravity center of the three states here, doublet E, doublet T1, and doublet T2. But actually, it should be not only 3 levels here, but it should be 4 multiplets, including quartet A2. And their calculation was based on OH symmetry, but our calculation will be with C3 symmetry. So in the work of Onishi Sugano, they interpreted R-line to the transition from quartets to the doublets. However, if we see carefully, doublet delta ER is the spin flip transition energy based on one electron calculation from T2G up spin to T2G down spin. That is a transition with spin states SZ half to SZ minus half. And this is actually just a reverse component. However, in the actual materials, the transition is occurred between spin state SZ3 half to SZ half. Therefore, delta ER should correspond to the gravity center of the 4 states here, including quartet A2. Then the transition from quartet A2 to quartet A2 is also considered. These are the calculation. I obtained this value from the reference here, Sugano, Tanabe, Kamimura books, multiplets of transition metal ions in crystal. We obtained the energy here, the left one, and we got the calculation like this. The relative energy is estimated from quartet A2 to each levels. These are the degenerate levels, and without considering quartet A2, we obtain the calculation like this. So it is the equation should be like this. But when we consider the quartet A2 for SZ half, then the calculation will be different. Okay, so now how to estimate the delta ER and delta EU? We introduce the Rogers transition state method. We will excite half electron for delta ER from T2G up spin to the T2G down spin, half electron. So we obtain the energy difference between T2G up spin and T2G down spin here with the pink one. And for the Slater's transition for delta EU, is simply by estimating 10 dq. It is the same. So we excite half electron from T2G up spin to the EG up spin also. We got the blue equation here. Next, these are the results for our calculation for R and U pan non-optimized cluster and optimized cluster, including this is for 7-atom model cluster. Okay, we introduce new formula here. You see the black symbols here are the experimental data, but our calculation will be the colored lines. Okay, then we see The agreement for the optimized cluster using 7-atom model cluster is better than the non-optimized cluster in the left side. The calculated R-line energies agrees the experimental data excellently. These are the result for 63-atom model cluster. We also perform additional calculation to investigate the tendency of U band and 10DQ. The calculations were performed by 7-atom cluster model with OH symmetry here by simple DBMA method. The results show that U band has higher energy than crystal field splitting. This is the real material C3 symmetry, and this is for OH symmetry. They are higher than the OH symmetry. So in any case, U band energy is higher, and the Onishi and Sugano results are just a simple estimation prediction from just 10DQ, but actually it's not. Next, we want to talk about how we predict the optical properties of manganese 4+ ions in alpha alumina under pressure. So there are the picture for molecular orbital energy for non-relax and using CASTEP. Yeah, it's increased like this. And here are the energy diagrams under pressure. Since we only have one experimental data at 0 pressure, therefore our results here are just prediction. But what we see here, the most important thing is in the case of doublet states, RR prime and B lines, they are decreased as the pressure increase, while for the quartet states, they are increased as the pressure increase. These predictions are similar with the tendency of Ruby. We also calculated the Coulomb integrals, Coulomb effective, and the results are similar, which implies that J effective is the main cause of the decreasing tendency of R-line energy. Next is the discussion for transition metal 3+ ion doped in alpha alumina. So we want to investigate the substitution effect of different dopant ions with the same ionic charge in the same crystals. We try to study how titanium 3+, vanadium 3+, chromium 3+, manganese 3+, ferrum 3+, and cobalt 3+, and we just have chance for a small number like vanadium 3+, chromium 3+, and manganese 4+, and also cobalt. Not for titanium and ferrum because we still don't have time. Okay, first one is the discussion for vanadium 3+. In the case of vanadium 3+ doped in alpha alumina, the pure one for lattice parameters are shown in the above, but for bond length in D1 and D2 are shown in the below. You see here when without dopant before lattice relaxation effect, it's 1.855 here, and it increased to 1.956. It's also the same happens with D2, 1.971, for after lattice relaxation effect, 2.079. This calculation was done by CASTEP method. Here is the molecular orbital MO energy of alpha alumina doped with vanadium 3+ for 7-atom model cluster in the left panel and 63 model cluster in the right panel. We see here when we consider lattice relaxation effect, the 10DQ decrease. Yes, but okay. Here the tables of their energy values. And we also perform the absorption spectrum here. The first peak is belongs to the triplet T2 states, and the second peaks belong to triplet T1 states. Since vanadium 3+ belongs to D2 configuration. So it is simply the transition from the ground state to their each state. Next, this is the investigation for molecular orbital energy of alpha alumina doped with manganese 3+. We compare 3 different lattice relaxation effects. The first one, non-relaxation, Shannon's, and then K-step. We get the results that 10 dq decrease in the order of non-relaxation, and then Shannon, and then K-step. K-step shows the smallest crystal field splitting, or 10 dq. Okay, and this slide shows you the absorption spectrum of alpha alumina doped with manganese 3+. Since manganese 3+ belongs to D4 configuration, then the transition energy for the peaks shown here are for the transition energy from 5e to 5d2. In this case, the experimental data was obtained for high spin state, but our calculation are for low spin states. And this one is the result for the molecular orbital energy of alpha alumina doped with cobalt 3+. The picture here, we compare non-relaxation, Shannon, and K-step again. It increases in the order of non-relaxation, Shannon, and also K-step. We just constructed using 7 atoms only. Okay, and here are the absorption spectrum of alpha alumina doped with cobalt 3+. For non-relaxation, we show here many peaks. Shannon's also shows many peaks here, but K-step model, we show only 2 peaks here. Experimental also shows only 2 peaks. However, in our calculation, once again, we just use low spin state, but the experimental data we have for high spin state. So actually they cannot be compared. Okay, and then this is the last part of my work so far. I want to talk about the chromaticity coordinates of ruby. Actually, we can calculate the color coordinates based on the absorption spectra that have been obtained from DVMA calculation. So after molecular orbital calculation using DVX alpha method, then we do calculation with DVX alpha method from multiple energies and then absorption spectra. So with that result, we can calculate color coordinate. Since the transmittance is expressed like this, okay, the intent T transmittance can be defined as a ratio between the intensity of incident light and the transmitted light. Then the absorbance can be expressed in the minus logarithmic function of the ratio of I and I0. Therefore, the transmittance T can be obtained by this function. Therefore, the 3 stimulus values X, Y, Z can be obtained by using this formula. P lambda denotes the standard illumination D65. Generally, the absorbance is proportional to the molar absorption coefficient, epsilon, the molar concentration of the particles, in this case, chromium ions, C, and the sample thickness, L. Therefore, a multiplication of the absorbance by a scalar such as A2 equals A1 lambda here means that the concentration and or the sample thickness are changed, so that C2L2 equals AC1L1 is satisfied. Finally, the color coordinate XY chromaticity here can be expressed like this. By using the 7-atom cluster model without considering lattice relaxation effect, without and with considering CDC-CC, we obtain absorption spectra like this, and we get the chromaticity diagram like this. We see here simple CI calculation and CI with correction, CDC-CC, agrees with the Ruby experimental data. Here is the conclusion. Okay, CASTEP can be used to estimate lattice relaxation and even the pressure effect. Okay, I think you can read the conclusion by yourself, and thank you very much for, if you want to contact me, you can contact me here in this email. And I'd like to thank all the committee members and also my university for supporting me and for the Distinguished Contribution Award winner. Thank you very much. Questions and advice are welcome.
Thank you very much for the interesting presentation. Now let's open questions and comments from the audience. Do you have any questions? Ishii-sensei, お願いします。
Okay, so Mega Sensei, thank you very much. Your presentation is very nice for us. My question is, one is pressure dependence. You have studied up to the 100 or 120 gigapascals. 120 gigapascal is what situation for use do you assume?
Okay, I will directly answer or waiting for another questions?
Yeah. Another question is effect. Can you calculate? Can you create a model with defect effect? Can you? Just finish.
Okay, Easy Sensei, thank you very much for the questions. I really appreciate, because sometimes when I talk in English, nobody asks. So it's really my honor. Okay, first about the, wait a moment, I will share the pressure slide. Okay. Okay, can you see this?
Sure.
Okay. So in the case of a pressure effect for non-optimized cluster, I just use Sonoma crystal structure from FIND-IT. There are many crystal structure data in FIND-IT, which includes the pressure effect. So I'm not sure, more than 10 I use here, more than 10 of crystal structure. But in the case of optimized cluster, using CASTEP code here, actually, I just want to make my models or make my calculation to be similar with what I have. I have only 1 to 113 GPA model cluster from FIND-IT. So that means in this case, the alpha alumina crystal structure is remain the same, not changed to the other materials like RH203. Yeah, because some too much pressure. I mean, like after 113 GPA, I once show the reference that it changed. The structure was changed. It's not alpha alumina anymore.
Okay.
Because too much stress.
So 100 gigapascal is a limitation for alumina.
Yes. Yes, limitation. After that, it changed the phase.
How about is my second question?
The second question is about defect effect, right? The defect effect, I've been trying when I was in Ogasawara lab, but actually since a little bit difficult, not easy, but not easy one, because when we consider defect effect, like I showed you before, there is mixing orbitals from impurity levels and conduction band. If that's happened, then I couldn't calculate CI calculations. I couldn't perform CI calculation. I can do CI calculation in the condition there is no mixing in impurity levels and in conduction band. So if there's no mixing, then no problem. But if there is mixing, then we have to think what should we do next.
Okay, so thank you.
Thank you, Prof. Issy.
Yeah.
ありがとうございます。杉原先生よろしいですか？
Yeah, I am very interested. Thank you, Professor Novita. And my question was exactly same as Professor Ishii. So it was solved. Thank you very much.
Okay, thank you, Professor Ishihara. Maybe I just published the results in Optical Materials journals. Maybe if you are interested to read more, or maybe you can download the paper, and also maybe if you're still curious about something, you can email me. So
Thank you. Thank you.
Yeah, I show you the list of my publication like this. It should be on 2020. It is in number 9 and 10. Oh, sorry. Yes, 9 and 10. 9 and 10. The number 9 here is the only for molecular orbitals calculation, but for number 10 here is the full CI calculation, multiplet energies, and absorption spectra. Now I'm in the progress of publishing one more paper about the color coordinates. So maybe later, if it is published, then please read my paper.
Thank you very much.
Thank you, Sensei.
よろしいでしょうか。はい、どうもありがとうございました。I'm very sorry to have to limit the interesting discussion, but we have to remain on schedule. So, everyone, could you...
塚先生。
時間
あと4分あります。
いいですか？
大丈夫ですよ。
はい、じゃあ、はい。他よろしいでしょうか？ご質問いかがでしょうか？Okay, so could you tell me your future plan of your research using the DVME method?
Oh yeah, Motozuka Sensei, thank you. So this year and the next year, just 2 years from now, I got research grants that should be carried out in the theme of rare earth materials. So probably this year and next year, I will focus on rare earth materials, relativistic with a DVMA method. And I also have another theme for research. So I do many research actually, because now I'm working in my university, not only in one department, but also 3 departments. So, you know, in my university right now, less doctor. So that's why I belong to many departments to support every department. So in the informatics department, I do some more programming, and in the science department, I will do more chemical research. That is my plan in the near future. But next, hopefully there will be another chance to have conferences like international conferences or national conferences, because I want to spread more and introduce more DVX alpha and DVMA methods. So now I'm collaborating with many researchers. Hopefully I can also collaborate with the members of DVX alpha society, because I'm pursuing a professor's degree in my university. It's actually still very, very competitive. It is very hard, but I try to survive myself here. And I'm so happy because of this year, I got these awards from DVX Alpha, and it motivates me to do better and better in the future. So this year, I try to collaborate with my friends, my colleagues in China and also in United States. So they are also were students in Ogasawara Lab. So it's going to be fun because we were the same year maybe. same age, not so different in age. So it will be easier to communicate. So I also welcome all of you if you have chance for me to join your research, or at least we can have a research grant together. My research fund, like applying for Japan country or Indonesia country. So next time, if we have opportunity to have research grant, I will inform you, maybe if we have time. Yeah, thank you.
Thank you so much, Dr. Mega. Okay.